So the solution, what would it be? First, let us see the bad guy who's making all this trouble. Actually, is the growth rate, which is linked to the productivity in grams per square meter per day, which is rather a low value here. This is so because of these factors that affect growth rate and productivity. For instance, insufficient irradiance levels due to the blockage caused by the growth of microalgae, because they absorb and block light. Also, deficient photosynthetic O2 removal. When microalgae do photosynthesis, they produce O2, which is toxic for them. So the O2 has to be removed. Another problem that may occur is the depletion of CO2. Another one is a poor temperature control and also contamination. The problem is that all these factors are interdependent and must be optimized simultaneously. In a practical situation, this makes that the microalgae concentration actually is no bigger than 0.1 to 1.0 kilogram per cubic meter of water. So this is a rather low value, which in order to get a good solution, it would be necessary to engineer at least a tenfold increase in algal concentration, for instance to 10 kilograms per cubic meter. So let us see how this could be obtained. The good guy. So let us look. Light propagation depend on attenuation. 2. Attenuation depend on algal concentration and phase fractions. Water, gas, and algae phase fraction. 3. Algal concentration depend on growth condition, and 4. Growth condition depend on light intensities and CO2 and O2 concentrations. So the solution would be to solve the photobiofluid dynamic coupling problem. That's the reason of our talk today. So let us look into some details of what this coupling would be. First of all, the so-called self-photosynthesis rate in function of the irradiance. How the intensity of light affects the photosynthetic rate. There's a very common and used model due to IBA 1982, which states that the growth rate μ is proportional to the intensity of light, and so the numerator here means that the higher the intensity of light, the higher will be the growth rate. But in the denominator, you have these as I and I squared grow. You will have a penalization in the denominator. So this is to mimic what happens in nature with this photoinhibition. I'm going to detail this further. But mu max is the maximum growth rate. K1 and K2 are constants that depends on the species that you're cultivating. So the curve, this curve here is shown in the figure. It has a growing region which corresponds to the activation phase of the photosynthetic units, and to a point in light intensity where growth rates start to decrease due to photoinhibition. This maximum here is given by this formula, and the intensity of light is given here. And let us look now. I'm going to detail this a little further, so I'm not going to give you many details now. But let us instead look on light attenuation, how light attenuates in function of the void fractions. we can state that the attenuation is proportional to the intensity of light. I is the intensity of light, gamma is the attenuation coefficient, and x is the distance from the light source. So this formula here means that attenuation is proportional to the intensity and proportional to the distance from the light source. This means that the more strong the light is, the more attenuated it will be. If we integrate this formula, assuming that gamma is constant, which is very reasonable in single phase flow, for instance, you arrive in this traditional formula here. But if we are working in three-phase flows, such as the case in our photobioreactor, we have a variable gamma, and if we integrate a model of how gamma would vary in function of the void fractions, for instance, we arrive at this formula here, which will be used further, and the parameters inside this formula are given here. The phase fractions, alpha WW, which is the water phase fraction, plus alpha BW, which is the CO2 void fraction, plus alpha PW, which is the microalgae phase fraction, when they all add to 1, actually. And assuming an equivalent attenuation model given by this is traditional for dispersed flow. In dispersed flow, you have let's start from the end. Alpha PW times gamma PW, which is the attenuation of the microalgae. Actually, this is the turbidity times the void fraction of the microalgae, plus alpha BW times gamma BW. Gamma BW is the attenuation of CO2 in bubbly flow, very small bubbles, okay, times its void fraction, plus gamma WW, which is the attenuation of water. Instead of using alpha WW, we replace this equation here, okay? So we have this equivalent attenuation coefficient, which can be integrated. Another parameter that appears in that last formula is the integrals here, which are given by this formula, okay? Actually, it's a cumulative void fraction. Some numerical examples. Okay, if we know a priori how these void fractions are, we can impose them. For instance, this formula, okay, which is quite a good representation of what happens in practice. Okay, so the red curve shows the gas bubbles void fraction, the CO2 bubbles void fraction. Okay, when you have the peak here of CO2, you have a valley of microalgae, which is the blue curve. Okay, so by integrating all these equations, we get the red curve, which is the intensity of light in function of the distance from the light source. Okay, all these are normalized value. The intention here was just to give an idea of the shape of this curve. It starts from 1, which is the maximum, and it goes almost to 0. Okay, the numerical values chosen here are quite representative of an actual situation. But going further, we can also integrate IBA's model now, replacing the intensity of light in function of the distance from the light source. Here we get the productivity rate in function of the distance from the light source. And when we replace all the formulas that we obtain here, we obtain this red curve here, which is also a normalized value, because the idea is just to give you to show you that you have 3 distinct regions inside a photobioreactor. You have a first region here, which is the closest to the light source, which is on the left border of the rectangle here. So you have an excessive illumination here, and the productivity is not very high. You have an adequate illuminated region here, where you have almost the maximum growth rate here. And a third region, which is the most distant one from the light source, where light is insufficient to have a good growth rate. So the curve starts to bend down here. Okay, let us move further and look another important aspect of microalgae cultivation, which is the so-called illumination darkness cycles. Photosynthesis can be viewed in a simplistic way through the so-called photosynthetic units. These units have three different states, or three possible states. The first one, called open or resting state, where a photon can stimulate transition to the activated state. And well, the activated state, where photons are captured, and depending on the amount of photons, two paths are possible. The first one, transition to closed state and start of photosynthesis, returning to open state afterwards. So it captures an adequate amount of photons, closes, and starts building biomass with these photons. And a second possible path, if the number of photons is too high, transition to inhibited state is done to avoid cell damage. This is a strategy to avoid cell damage. Okay, and in the inhibited state, it can eventually return to open state after a period in the dark. Okay, so this is represented here. The photon is captured by the PSU, the photosynthetic unit. If the amount is adequate, it transitions to the activated state, where it receives a little more photons. It then closes, and biomass is produced. If the amount of photons is too big, transition occurs to the inhibited state, and if the cell passes some time in dark, it can transition back to the open state. Okay, so what happens in the photobioreactor is something like this. This is the light source, the excessive illumination region, adequate illumination region, and sufficient illumination region. When you inject the CO2 here, depending on how you inject this CO2, you can produce recirculation, which is an interesting thing to occur, because the cells that passes too close to the light source, they will very likely become inhibited, and they can pass some time in the dark here in order to come back to the active state. Okay, and when they pass by this adequate illuminated region, they can capture some photos and produce biomass, because if they close around this region here, they will be producing biomass while passing by the second time too close to the light source. So this is something interesting to have in the photobioreactor. But you see that things are becoming coupled now. How you inject the CO2 affect the flow field, which affect recirculation, which affect how much time each particle or each cell passes in one of these three different regions. So all these are a coupled problem. A very beautiful study of the illumination darkness cycles were due to Machuk and collaborators. I captured some of their the results here just to explain that they build a small photobioreactor and illuminate it with an intensity of light that vary like this, as in square waves. Okay, the total period is Tc, and the total illuminated time is TL. Their experiment, they maintain a constant Tc for 45 seconds, and they varied the amount of time that the photobioreactor was illuminated. What happens in the PSU supposedly is that it becomes activated for some time. Then when the lights go down, they become inactive. Okay, so when the light goes up, it becomes activated, produces biomass, and then it rests here. So their study they started varying the intensity of light, like 50. You see that with the smallest intensity of light, you have a positive biomass production after 35 seconds of illumination time. Okay, if you increase a little further the intensity of light to 110, the amount of time that you have to illuminate in order to have a positive biomass is now around 20 seconds, compared with 40 seconds, which is the whole period. If you increase further to 220 the intensity of light, now the period of time that you have to set in order to have a positive biomass production is around let's see 12 or 13, something like that. You have I forgot to point that you have a higher maximum productivity here at 220. But if you increase further the intensity of light, things start to change. From 220 to 1000 to 550, you see that the maximum productivity decreases. Okay, and the TL, the time that you have to spend illuminating in order to have a positive biomass production, decreases a little bit. If you increase a little further the intensity of light to 1000, the maximum growth rate decreases even further. Okay, and at 2000, you don't have any more positive biomass productivity, because you're having a lot of cell damage in this situation. So this shows that things are quite complex actually, and a very likely operation in an optimized photobioreactor would be something like this. At low algal concentration, it would be interesting to set a low light intensity and small CO2 flow rate evenly injected on at the bottom of the photobioreactor. At intermediate algal concentration, it would be interesting to increase illumination intensity and CO2 flow rate, starting to concentrate injectant near the light source in order to induce recirculation, because you're going to start having inhibition in this phase here. A third operational situation would be at high algal concentration. It would be interesting to set light intensity and CO2 flow rate to the maximum, and to concentrate CO2 injection near the light source in order to protect against cell damage to excessive illumination. So the optimal design and assisted operation would require to set illumination intensity and CO2 injection profile. These 1, 2, 3, 4 are the steps in a procedure in order to optimize the design and or the assisted operation of the photobioreactor. So step 1 would be to set illumination intensity and CO2 injection profile. 2. Solve the 2 or 3 phase flow field. That would require an online CFD. Third step would be to calculate the phase fraction profiles and to upgrade growth condition. This is not a simple task to do. And 4, determine ideal illumination intensity and CO2 injection profile and return to step 1. To do this fourth step, it would be necessary to solve an inverse problem. And voila, that's the murderer revealed. It is necessary to solve an